All right, so a man 6 feet tall walks at a rate of 2 feet away from a lamppost that is 12 feet high. What is the rate, or at what rate is the length of his shadow changing when he's 55 feet away from the lamppost? So the first thing I'm going to do is I'm going to draw my little lamppost. A perfectly drawn lamppost. And that thing is 12 feet high. All right, and the man is 6 feet tall, so we'll draw our little guy here. And remember that he's 6 feet tall. And the lamp will cause him to kind of cast like a little shadow. Well, we'll do it like this. Okay, and so when we think of this, this is kind of a lot like, this is like a right triangle, right? So I've got this thing here, and it goes like this, and then boom. All right, so now let's label some of this stuff. This line segment here is 6 feet. This line segment here is 12 feet. Do we know how far away from the lamppost he is? Well, kind of. But let's start. Let's label some stuff first. First of all, the distance he is from the lampshade is we'll call it x. And then we'll call this distance from here to here, we'll call that s. So we'll call that the length of his shadow. And that's the question that we're asked is, at what rate is the length of his shadow changing? So what we're curious about is we want ds dt, because this all happens with respect to time. And he's walking away at a certain rate, and that has an impact on his shadow. So the first thing that we want to do is, does it give us a rate that he walks away at? In other words, yeah, it does. It says 2 feet away. So this is actually dx dt. That's the rate in which he walks away, is equal to 2 feet. Okay, that's good. I'm just randomly going through and labeling things. And then we're told that x equals 55 feet. And so let's think about this. We have similar triangles. So I have one triangle that looks like this, right? The little triangle, which is 6 by s. And then I have another triangle that's 12, and then x plus s. Does that make sense, you guys? And then the only other thing is maybe, yeah, so those are similar triangles, so they should be proportional to each other. And so we'll write these as being proportional to one another, and then we'll have an equation. Take the differentiate implicitly, and then when we differentiate implicitly, then we'll be able to then we'll be able to, oh, dang it, what did I say S was the shadow, right? Mm-hmm. Then we'll be able to solve for ds dt, all right? So because they're similar triangles, I'm gonna write this over here in this little box because I don't have a lot of room left on the screen. If I compare s, that compares to s plus x. And then s over 6, that's a small triangle. What do I put here, you guys? 12. All right, so now what I want to do is I want to cross multiply and solve, and then take the derivative and stuff. So I get 12s is equal to 6 times s, so I get 6s here, plus 6x. Now one little trick that we do is if I subtract 6s from both sides, I get 6s is equal to 6x. Okay? And if I take the derivative of this, and I could go so far as to really, truthfully, just divide both sides by 6 and I get s equals x, right? So if I say s equals x, then when I differentiate both sides, the derivative of s is what? 1 ds dt, right?
Oh, okay.
ds
Because
dt
s is taken with respect to time.
dt is equal to, the only thing that bothers me, okay, and then for x I get dx dt. The only thing that bothers me, oh no, that's right, dt. Now, we got ds, which is what we're solving for, is equal to dx, or ds dt is equal to dx dt, but what's dx dt?
Dx dt, we said that it's 2 feet.
It's 2 feet. So I think this whole thing is 2 feet. Now the numbers will change on the test, so make sure that you go through all this stuff. Don't think that it's just a coincidence that they're the same number. They're just the same number because the computer arbitrarily chose values where I've got this ratio of 1 to 1. Sometimes this number might be 5 and the other one might be like 3 or something, so you get a ratio. So I think it's A, right? Yeah.